recording. There we go. All right, so let's start with a quick recap. Yesterday we looked at the work energy theorem. The work energy theorem basically tells you, since I'm going to do the example 2, I'm going to put it right above it. So we're doing example 2 on AS 3-11 today. So let me create a little room here. So we looked at the work energy theorem. The work energy theorem is basically a statement of law of conservation of energy, which takes into account the work done by external forces. Okay? What it really says, it says that the mechanical energy, the initial mechanical energy of a system, start with that. And then if there is work done by any external force, then add that work done. The work done by an external force may add or remove energy. So it could be positive or negative. So work done by external forces added to that. When you add that, that gives you the final mechanical energy of the system. So if there's no external force, if for example, in a problem where, like the roller coaster problem, where there was gravity was internal because gravity is part of the mechanical energy there, right, in the form of potential energy. But if there's no external force, such as friction, external force could be some outside force, such as some sort of an applied force. If there's no such force, then the mechanical energy does not change. The sum of the kinetic and potential energy is the mechanical energy. That remains constant. But if some external force is doing work, such as friction, then part of the mechanical energy will go into heat. So your final mechanical energy will be less. If the external force is doing positive work, such as maybe some applied force is putting energy into the system, then obviously the final mechanical energy will be greater than the initial mechanical energy. And we can also write out the formula ME. Remember, mechanical energy, the shorthand being ME, is the sum of KE and PE. So the initial mechanical energy is initial KE plus initial PE plus the work done by external force equals ME final is KE final plus PE final. Okay. And then the other thing you need to know when you're solving these problems, you need to know the formula for kinetic and potential energy. So let me also write that down here. We're going to use all of this stuff. So kinetic energy, the general formula is a half mv squared. Potential energy, the formula is mgh because it depends on height. And the work done by external force, or just the work done, is that external force that's doing the work, the absolute value of that, times the displacement, times the cosine of the angle between the external force and displacement. All right, now we're going to use these formulas. We have this, and this, the third line is a breakdown of all that. All right, so in every problem, first read the problem and try to picture what's going on. Sometimes diagram helps. Identify an initial position, identify the final position, and and then look at your formula, which I'm gonna put an asterisk. This is the formula we're dealing with here, and throw out any terms that are zero, and then solve. Okay, so let's read this problem. This is example 2. A weightlifter applies 1,000 Newton force to raise barbells by 0.25 meter at a constant speed. What is the work done by external force? What is the final mechanical energy of the barbell if the initial potential energy is 1,500 joules? Okay, you can do this problem even without looking at this equation, but I'm going to show you just so that you know how to use the formula. I will show you how to use it, and then we'll have a discussion which will reveal to you the shortcut. Those of you who are getting better can take the shortcut. All right, there are 2 things we're calculating. We're asked to calculate the work done by external force. So let's make a list of all the known and unknowns. So this is what we're asked. What's the work done by external force? The weightlifter applies 1,000 Newton force. So he is lifting the barbells using this force. If he is applying a constant force, then that means that the force he's applying must be equal to the weight of the barbell. So the barbells weigh 1,000 Newton as well. But anyway, that's the force that he's applying. And he lifts the barbell by the displacement, which is also the height, right? In this case, height and displacement are the same thing. I'm going to put it as delta x is 0.25 meters. You'll see in a minute why. What is the work done by the external force? So W external equals question mark. And what is the final mechanical energy of the barbell if the initial potential energy, so PEI, is 1,500 joules. And we also want to find ME final. What is the final mechanical energy? Okay. All right, I'll tell you what, let's change this to, instead of final mechanical energy, let's look for the final potential energy. Can you change that? I'm going to change the wording there. Let's look for the final PE. Okay. So PE final equals question mark. All right, so here's the barbell. It started initially here, and then it's lifted by that height, delta x. Delta x is the same as height, right? And the force applied, F, is given, which is 1,000 newtons. And it's moving at a constant speed. So now let's pay attention to the work energy theorem, this formula here. And let's see what we can throw out. Any problems where, let's say, kinetic energy doesn't change? If the kinetic energy doesn't change, then this term and this term are going to have the same value. If you have two numbers, that same number appears on both sides of the equation, and it's adding on both sides of the equation, you can simply get rid of it by subtracting it. So let's throw out, let's subtract, let's get rid of KE. Anytime KE does not change in a problem, you can just throw it out. Anytime potential energy doesn't change in a problem, you can also throw that out. Keep that in mind. Anytime something is not moving, you can throw out the kinetic energy. Let's say if something is at rest to begin with, then KE initial would be 0. If something stops moving, then KE final would be 0. So you can use all of that. If something starts at 0 height, then PE initial would be 0. Similarly, the new thing I just introduced to you is that if anytime the KE initial and final are the same, you can throw that out because they're just going to cancel each other out. You can just subtract that from both sides of the formula. All right, what else can we throw out? Initially, does something has potential energy? Yes, it does. So we cannot throw that out. That term needs to be kept. Is there work done by external force? Yes. The force that's lifting the barbell is the external force. So we can't throw the W term. PE final is what we're looking for. Okay. So now let's do the calculation. So that's the formula that I have left. So I'm going to write that out. I'm going to get rid of this diagram because it's going to get really messy. So let me just do the calculation. Now I'm going to plug in these formulas into the work energy theorem. PE initial. The first term that I have is PE initial. In other words, this one. So that is going to be, that's already given to us. It's 1,500, right? So keep it as PE initial and put the term, put the value in there for PE initial. That's 1,500. Plus W external. We don't have W external, but you can use the formula here to calculate it. I'm going to just put that in there. It's F, the force. So I'm going to calculate this by substituting it in here. Let me add an extra step here. I'm going to first write down F delta X cosine theta, and that's going to give us P final. Now I'm going to plug in. Okay, 1500 plus the force is 1000 newtons. Displacement is 0.25. The cosine of the angle. Does anyone know what the cosine of theta is going to be? The external force is an applied force. It's acting up. The displacement is up as well.
0.
Exactly, 0. In other words, cosine of theta would be a positive one. There's positive work being done. So cosine of 0 should give us PE final. Okay. Now, now you just simply calculate. I'm going to flip the equation around. So I'm going to write that as P final equals, so it's 1500. All you do is just do 1500. You basically, this here is 1. Okay. So if you calculate that, you should get, I'll give you the final answer here in a minute. That should be, so that whole thing should turn out to be 250 because cosine of theta is 1.25 times 1,250. So let me just do it in one step. It's not such a difficult algebra to do. So P final is just going to be 1,750 joules. That's the final potential energy. Now, if you wanted to find the mechanical energy at the very top, when somebody lifts up a barbell, then they're holding it still at some height. If they're holding it still, then all the mechanical energy is in the form of potential energy. So that would be, the problem doesn't clearly specify whether, it's still moving or not. That's why I just changed it to potential energy. But if as weightlifters do, they start at sometimes they're holding the barbells in their hand, maybe close to their knee level, and then they suddenly apply, they'll apply a force, and there may be some point where there is acceleration. In this case, we're told it's moving at constant speed, and then they're lifted up to a height above, and then they hold it there, right? The weightlifters will sometimes hold it up there and hold it for as long as they can, and then just drop it. So in that case, your mechanical energy would also at the very top be P final energy at that point. Because if it's holding it there, if he's holding it there or she's holding it there, then that's also mechanical energy. But anyway, that's the final potential energy. One way to think about that is this. The weightlifter started with this initial potential energy. So obviously they didn't start at the ground level. They were holding the barbell maybe close to the knee level. Then they did work. By doing work, they added energy. How much energy did they add? This equal to the work done, which is about 250 joules. And then when you add that to the initial potential energy, then that gives you the final potential energy of the barbell at that new height, at 0.25 meters above that starting point. All right, any questions on this? Does that make sense then? All right, so let me stop the recording here. I'm going to pause the recording. We're going to go over another problem as well. All right, let's look at question number 3 now. Oops. So again, to begin with, as you can see now, I have the work energy theorem written here. What you got to do is look at the problem, ask yourself, what's the initial position? What's the final position? Which of these terms can be thrown out because of being 0 or because of being equal and stuff, and then proceed. So 1,423 kg car is moving along a level highway with the speed of 26.4 meters per second. The driver takes the foot off the accelerator and the car experiences a retarding force of 901 newtons over a distance of 106 meters. Determine the speed of the car after traveling this distance. So the question at hand is this. Okay, first of all, there is an external force. The external force is, it says, a retarding force, which means some sort of like friction or overall, is going to slow down this car. Somebody just takes off the foot from the gas. So that's your F. So let's write that down first. So F is 901. It's going to do negative work, right? And over what distance does this external force act? Over 106 meters. That's the displacement of the car. The car has a mass. Up here it says the mass is 1,423 kilograms. And it's moving at an initial speed, VI. So VI is given 26.4 meters per second. And it says determine the speed of the car after traveling this delta X of 106 meters. So VF is what we're looking for. Now look at your equation. This entire problem deals with a car moving at the same height. It doesn't say anything about the car changing its height above the ground, right? It's not going uphill or downhill or anything like that. So potential energy does not change. If potential energy does not change, we can call that as a zero, that level as having zero potential energy. That term, PE term, drops out. Even if it was at some height, PEI and PEF are going to be the same, right, throughout the problem. So you can just cancel them out. Do we have KE initial? Yes, the car is moving initially. Do we have W external? Yes. There's this retarding force that is slowing the car down. That's going to do the work done. That's the force that's doing the external work. And then we are looking for KE. We're looking for V final. So there is KE final. All right, now let's write down the formulas for KE and W in that. Plug those formulas into the work energy theorem. KE initial is half mv initial square. That's basically just substituting the formula for KE down here. That's half mvi squared. Plus, now let's look at the next term, which is the external work. The work done, remember, is F delta x cosine theta. The absolute value of F delta x and cosine theta. Last of all, we have K final, which is going to be half m v final square. See how it is important that you put VI and VF where needed. Otherwise, if you just have V on both sides, then you're not going to know which velocity we're talking about. There are two different velocities. Or in this case, it's speed. Velocity, really, the direction doesn't matter for these formulas, only the speed matters. Now, in this problem, notice that you cannot cancel M. You know how we did that example yesterday where M canceled out? M will only drop out when there is no external work done by external force. But if there is work done by external force, then you can't get rid of M. So you have to keep that. Let's plug in all the numbers now. So then we have half times M, which is 1,423, times V initial, which is 26.4. You take a square of that, this thing, plus F, which is 901, times delta X, which is 106, times cosine. Remember, if a force, this force is a retarding force, this is a frictional force, so it's acting in the direction opposite to motion. It's opposing motion. So the angle should be 180 degrees. And remember, cosine of 180 degrees is -1. If you remember that, you don't even have to write cosine 180. You can just put a -1 there. And then you're going to set that equal to half m, which is 1,423, times VF is what you're looking for, so keep it as VF with a square. Let me pause here and ask anybody if you guys have any questions on this setup. So any questions on substitutions or any setup of this? Okay. Now you got to do what you got to do is calculate. So first you're going to multiply all these out with a square on 26.4. This term, because of the cosine of 180 degrees, you're going to subtract 901 times 106 from that. Then on the other side, you're going to take half of that. Okay. And then you are going to calculate VF. I'm going to leave you to do the algebra. Eventually, you're going to take a square root. So first, the two terms on the right side, you're going to subtract those. And then that's going to equal half of 1,423. Then you divide by whatever you get by taking the half of 1,423 and take a square root. That's what's going to give you 23.7. I want you to do this algebra in your time so you know how to do it. If you didn't get this, if you made a mistake in the algebra, then ask for help. But I'm going to leave the algebra to you. Any questions at this point? So that's basically how you're going to solve these problems. We're going to do a few more together the way we did this. So the next one I want you to do, still got a decent time here. I want you to try number 2 now. Go to number 2. Let me just pause this recording now.